A chemical change occurs when two or more substances come together and the atoms that make up those substances are rearranged to form a new thing. In Chapter 3, we'll take a look at chemical changes, or sometimes called chemical reactions, and how mathematics can be used to calculate many of the changes that occur in these chemical changes or reactions. First, we'll start with section 3.1 called chemical equations. Chemical changes can be represented by what's called a chemical equation. Not a mathematical equation, but an equation that uses symbols from the periodic table to illustrate how the atoms are changed or rearranged. In this, an example of a chemical reaction, we have things called reactants on the left side of the reaction, and then there's an arrow that means yields or produces or makes or forms, and then we have the product or products on the right hand side of the reaction. Reactants are always on the left, products are always on the right, and they're always separated by an arrow. Always separated by an arrow, and we'll learn next year actually that sometimes we use a double arrow to illustrate that, one going forwards and one going backwards. But for right now, we'll just look at one going from left to right. We always read chemical reactions from left to right, just like we read a book. And we always call the reactants the things on the left and the products the things on the right. We use symbols from the periodic table to illustrate what the chemicals are that react and the chemicals that are produced. And we use small symbols such as S, L, G, and AQ to illustrate the phase of matter that those reactants and products are in. If it's an S, it stands for solid. If it's an L, it stands for liquid. If it is a G, it stands for gas. And if it's an AQ, that stands for aqueous, meaning dissolved in water. Dissolved in water. Aqueous means dissolved in water. So you can see in this reaction we take hydrogen in its gaseous form, react it with oxygen in its gaseous form, and we get some liquid H2O or liquid water. This is an example of a chemical reaction with products and products on this side, reactants on this side. So in chemical reactions, we many times have these numbers that are in front of a reactant or in front of a product. These numbers are called coefficients, and coefficients can be distributed in, that's using a math term now, to illustrate how many of each item we have of a particular reactant or product. For example, this 2 speaks to the hydrogen, and since there's a small 2 representing that there's 2 hydrogen atoms, it's 2 times 2 or 4 total hydrogen atoms. Over here on this side, this 2 distributes in not only to the hydrogen but also to the oxygen, and it illustrates that there would be 4 hydrogen atoms on this side and 2 times 1 or 2 oxygen atoms on this side. So for an example question that uses a coefficient, look at this one. How many atoms of Mg, O, and H are represented by 3 MgOH2? And notice there are parentheses around the OH, meaning that this small 2 right here actually speaks to everything inside of these parentheses. So the 3, remember, like I said, has kind of like a distributive property, and it speaks to the magnesium. It also speaks to the oxygen, and it also speaks to the hydrogen, and it's distributed in evenly. So there would be 3 magnesiums in this, 3 magnesiums, and 3 times 2 oxygens, because remember this 2 distributes into everything that's in the parentheses, so there would be a total of 6 oxygen atoms in there, and 2 times 3 for the hydrogen, meaning there would be 6 hydrogen atoms in here as well. So get used to using these coefficients right here to illustrate how many of a particular formula unit there are in a particular chemical reaction. A long time ago there was a scientist that said that there is something called the law of conservation of matter. The law of conservation of matter said that matter is neither created nor destroyed, it's just changed from one thing to another, or rearranged as we have in a chemical reaction. Let's take a little inventory of this chemical reaction and see if anything has changed from one side to the other, and if we have conserved the atoms from one side to the other. Taking a look here, how many hydrogens are on the left side of the reaction? Well, there's 2 of them. This 2 speaks to this H. And there's 1, 2, 3. Oh, 3 hydrogens on this side. Something's wrong. Look at the sodiums though, and there's 1 sodium on this side. There's 1 sodium on this side. There are one oxygen on this side of the reaction, this entire side of the reaction, and there is one oxygen on this side. So it looks like the sodium and the oxygens are correct, but does this mean that the reaction is written incorrectly? It doesn't obey the law of conservation of matter. I have more hydrogen on this side of the reaction than I do on this side. Am I breaking the law of conservation of matter, or did I just prove that there is no such law as the law of conservation of matter? Maybe it was a lie. Well, it turns out that the law of conservation of matter is true. But the way that we illustrate that there are the same numbers of atoms on one side and the other is by doing something called balancing a chemical reaction. And balancing a chemical reaction is where we take coefficients, numbers like this 3 we had right up here, numbers like this 2 that we saw right in front here, or this 2 in front here, and we use those coefficients to even out and make sure that we have the same number of hydrogens, sodiums, and oxygens on both sides. Now, coefficients can only be placed in front of, not in between, not down below, not in the middle of, but only in front of a reactant or in front of a product. You cannot put a coefficient or a number in the middle here. You can't add a subscript down below. The only way you get the subscripts, of course, is from the things we learned in Chapter 2, where we match up the charges and drop and swap them from one side to the other. In this particular case, when we're balancing and applying the law of conservation of matter, we can only add whole number coefficients in front of the reactants or the products. And so in this case, I notice I have 3 hydrogen on this side and I have 2 on this side. So to balance this, somehow I've got to get an even number of hydrogens. So what I'm going to do is I'm going to place a 2 in front of this NaOH. How did I know to place a 2? Some people don't like the answer to that question. The answer is, I guessed. And that's the thing that some people don't like about balancing a chemical reaction, is it takes trial and error to make it work. Now, I'm just guessing that I'm going to need a 2 here because this will give me 2 hydrogens. Remember, the 2 distributes all the way in here, plus 2 more, so a total of 4 hydrogens. But it also changes my number of sodiums and my number of oxygens, which you were probably jumping up and down and saying. It changes my sodiums to have 2 sodiums, and it also changes my oxygens, so I have 2 oxygens on this side. But when I balance a chemical reaction, I can place more than one coefficient in a reaction. As a matter of fact, since I changed this to 2 sodiums and 2 oxygens, I better go over here and put a 2 in front of the sodium, so then I have 2 sodiums on this side as well. And I actually have this number of sodiums now back to balanced, 2 on this side and 2 on this side. I could also place a 2 in front of the water right here, and now I have 2 times 2, or 4 hydrogens. Ooh, the hydrogens are now balanced as well, and 2 times 1, or 2 oxygens. So 4, 2, 2, and 4, 2, 2. I've now balanced my first chemical reaction. Notice there's now a 2 in front of the sodium, a coefficient of 2 in front of water, a coefficient of 2 in front of NaOH, and since there's no number written right here, I'm assuming that it is just a 1. If you don't see a number written in front of a reactant or product, always assume that there's a 1 there, and you don't need to write that 1. It's just assumed that it's there. Here's a second example. Let's take an atom inventory, and this is how you should begin balancing reactions, by taking an atom inventory of both sides of the reaction. How many ions are there on both sides of the reaction? Well, on this side there's 1, and on this side there's 2. How many oxygens are there on both sides of the reaction? Well, there's 2 on this side and there's 3 on this side. So you'll notice that I have twice as many ions and more oxygens on this side of the reaction than I do on this side. So somehow I have to get them balanced out. So I've got the same problem, an odd and even problem with the oxygen. So I'm going to double this side to start with, which gives me 4 ions now, and 2 times 3 are 6 oxygens. Now maybe I can make this work. Let's try a 3 in front of the oxygen, because now that gives me 6 oxygens. And let's do a, how about a 4 in front of the iron, because that gives me 4 irons. 4 and 4, 6 and 6. There's another balanced chemical reaction. How did I know how to do it? I had to guess. I had to guess, trial and error, and you'll get plenty of that type of practice in class. Taking an atom inventory is the key, and making sure that you list the number of products and the number of reactants and saying how many there are allows you to easily see if you can balance or make the same on both sides of the reaction, the reactants and the products. Section 3.2, some simple patterns of chemical reactivity. There are 3 different types of basic chemical reactivities that Chapter 3 looks at. In Chapter 4, we'll look at 3 much more broad classifications, but these are just some simple ones that you get to learn in Chapter 3. The first one is called combination, or sometimes it's called synthesis. And this is when we have one type of atom or element coming together with another, and it produces one product. Like, for instance, X coming together with Y to make XY. An example of this would be if we had H2 coming together with O2 and making some H2O. This is a combination or synthesis reaction because we synthesized or combined 2 things to make water. Now, of course, I'd have to balance this chemical reaction, which I did up above. I actually had this reaction up here, a 2 in front of the H and 2 in front of the H2O to make it a balanced chemical reaction. The second type of reaction, simple pattern of reactivity, is something called a decomposition reaction. This is the opposite of composition or combination. I should put that in here as well. Sometimes this is called combination or synthesis, or sometimes it's also called composition. Composition, synthesis, combination all mean the same thing. The opposite of composition, synthesis, or combination is called decomposition. This would be where we have one thing and we break it up into 2 or more. For example, we take water and we break it apart into its constituent elements, hydrogen and oxygen. This is called the decomposition of water, and we'll do this one as a demonstration in class. It's called the electrolysis of water. And of course, I'd have to balance this once again, and I'd have to have a 2 here and a 2 right here to balance it. And I could put in the states of matter here as well. This will turn into a gas, this will be a gas, and this would be liquid water. This is called a decomposition, where we have one thing and it breaks up into 2 or more. It doesn't necessarily have to break into its elements. Like, for example, one thing that we do in the laboratory is take the compound KClO3, KCl, I probably didn't get that L in there very good, but it's KClO3, and this breaks apart into KCl and oxygen gas. This is a good way to produce oxygen gas in the laboratory. Go ahead and try to balance this decomposition reaction. KClO3 breaks up into 2 other things. Notice it doesn't necessarily break into just its elements. It breaks up into a compound and another element. The last type of simple reactivity is called a combustion reaction. And a combustion reaction is one where we combine something with air and it produces flame, or it burns. It's a rapid reaction that produces flame and perhaps smoke as well. The general combustion reaction that we talk about mostly in chemistry is where we take something that has carbon, hydrogen, and maybe oxygen. I'll just put it in the dashed circle here because it doesn't necessarily have to have oxygen. And there can be a certain amount of carbon, a certain amount of hydrogen, and a certain number of oxygens. And we combine it with oxygen from the air and we burn it. And it always has the same 2 products as long as we have an excess or a large amount of oxygen in the air. It produces carbon dioxide and water. Carbon dioxide and water are always the products of a hydrocarbon combustion reaction, or a carbon-hydrogen-oxygen containing thing that burns in oxygen. There are other things that burn in oxygen as well, like, for example, sulfur could burn in oxygen. That would also be considered a combustion reaction if it was producing flame. It would produce sulfur dioxide then as well. Here's an example of a combustion reaction that's actually kind of tricky to balance. Let's take C2H6, which is known as ethane, and let's burn it in an excess or a large amount of oxygen from the air, and we'll make our 2 products that we always do, carbon dioxide and water, and you should memorize that these are the 2 products always of hydrocarbon combustion. If there's not enough oxygen around, then you get some of those nasty products around that you don't really want. For example, in the wintertime in Minnesota, they tell you not to start your car and leave it run with the garage door closed inside the garage for a long time. And the reason is because then you'll run out of oxygen, because of course gasoline is a hydrocarbon containing thing and it's going to produce carbon dioxide and water. But if you run out of oxygen, you're going to produce something called carbon monoxide along with this as well. That's if you have a limited amount of oxygen. But we're going to assume that we have lots of oxygen. We'll just put a little excess down here, and it's in a gaseous form, so we'll put a little G down there. The C2H6 is also a gas, and then the carbon dioxide that we form is a gas, and the water we'll say it's water gas as well. We'll just say it's at a higher temperature. Anyway, to balance this chemical reaction now, of course, we'd take an atom inventory and we'd say how many carbons are there on the left side, and there's 2. How many are on the right side? Well, there's 1. How many hydrogens on the left side? Well, there's 6. How many hydrogens on the right? Well, there's only 2. And then how many oxygens are there on the left side? Well, there's 2. And how many oxygens on the right? Well, there's 2 plus 1, or 3. Notice that we've got that odd even oxygen thing going here, which makes it kind of tricky to balance once again. Well, when you balance combustion reactions, the general rule of thumb is to first balance the carbons. First balance the carbons. Then take and balance the hydrogens. And then when you're all done, see if you can balance the oxygens, and I'll show you a trick to balance the oxygens in this one as well. And that's the general rule of thumb with balancing anything. Always balance the things that are present the least on both sides of the reactions first, and then balance something that appears more than once last. In this case, we have oxygen appearing once on the left side, but twice on the right. And you'll notice also carbon only appears one time on both sides. Hydrogen only appears once on either side as well. Even though I wrote this as HOH, it could be written as H2O, and it'd only be in one compound. So anyway, balance the carbons first. Let's put a 2 here. So that gives me 2 carbons. That also gives me 2 times 2, or 4, plus 1 more, 5 oxygens. Next, balance the hydrogens, and I have 6 of them on this side, so I'm going to have to end up with 6 here, so that's a 3. That gives me 6 hydrogens on this side. 3 times 1 times 1, or 3 times 2 is 6. So now I've taken care of that, but I've also mixed up my oxygens again. I have 4 times 2 giving me 4, plus 3 more is 7. I now have 7 oxygens. And I've got this odd even oxygen thing going here, which makes it really difficult to balance, because what times 2 is equal to 7? Well, it's not a whole number. It'd be like 3.5, right? But here's an easy way to balance these difficult combustion reactions. Go ahead and write 3.5 in there. I know. I told you it had to be whole number coefficients. But just for now, go ahead and use a half. Go ahead and use a half. Because now, when I multiply this by 3.5, I end up with 7 oxygens, and the whole thing is balanced. No, 2 and 2, 6 and 6, 7 and 7. And in Chapter 5, we'll actually find out that you actually can use halves and thirds and quarters sometimes to balance a chemical reaction, but it's kind of rare. Anyway, to stick with the rule of thumb that we should use whole number coefficients, what I could do now is take the entire reaction and double it. Multiply the whole thing by 2. Which means I'd take this 2 and distribute it in and multiply it by each one of the coefficients. And if I take this and multiply each one of the coefficients by 2, I now end up with a chemical reaction that is 2C2H6 plus 2 times 3.5. Oh, now it's a 7. Look at that. It's a whole number. Yields 2 times 2, or 4 CO2s, plus 2 times 3, or 6 H2Os, or HOHs. And you can see now, if I take an atom inventory of both sides, the oxygens on the left side are 14. On the right side are 8 plus 6, or 14. My hydrogens are 2 times 6, or 12 on this side. 6 times 2, or 12 on this side. And my carbons, I have 4 here and 4 here, and the entire reaction is now balanced. That's a trick to use when you're doing combustion reactions, especially if they have an even number of carbons and they end up being kind of strange on the right hand side and you can't get them to balance. So chemical reactions, ladies and gentlemen, once again, chemical reactions are changes of and rearranging of atoms. They're represented by a chemical reaction with reactants on the left, products on the right. And to obey the law of conservation of matter, you need to learn to balance a chemical reaction, making the same number of reactants on one side as on the product, obeying the law of conservation of matter. Good luck with your chemical reaction writing and balancing.